All right, so as with my other courses, this is going to be licensed Creative Commons. I have this in for public release and copyright waiver, so eventually this will be something you can just use in any venue. All right, and this is what we're going to be learning in this class. Need like a pointer or something. So, you know, this looks a bit overly complicated. It's actually, so this right here, this is all duplicative, but this right here should have a bunch more detail on it. So it is actually this complicated. Yep. And if you took intermediate x86 already, you get the joke. Otherwise not. All right. So I realized after I taught the last x86 class why I put generalist, not specialist. I mean, I said last time that it's because I do think there's value in being a generalist and not getting just into a single niche. But it's also just so I can, you know, have a cop-out and be able to say, if I don't know something, it's because I'm a generalist. I'm not a specialist in this. And so all of this is stuff basically that I had to learn for work. So I found that there was value in it for a bunch of different areas other than what I learned it for. So that's why I wanted to pass it along. All right. Now we're going to do the standard thing of just introducing yourself. And remember, I know most of you, so it's really just introducing yourself to the other people in the room so they can know who else is here. You know, some people maybe had compilers classes, but you know, even the people who had compilers classes, they told me that most of their class was focused on the front portion of what we're going to be talking about. It's just the lexing, the parsing, and things like that, how you actually break down the high-level language into well-structured control flow graphs and things like that, context-free grammars. But they didn't do as much with the actual taking whatever data structures they created and then outputting real code. And so that was part of one of the things that I wanted to talk about here, because I haven't taken a compilers class, but I'd known enough from like automata theory classes about context-free grammars, regular expressions, and all that. And so I wanted to actually show how real assembly code gets spit out of, you know, the data structures that get created from the parsing of things. So this is our rough format. Okay, and then, like I said, I went completely over. It's clear now that I have like 3 days worth of material in these slides, which it was pretty clear when this part 2 started getting around like 150 slides or whatever. But we're going to basically, what we're going to try to do in this class, and this is partially also so that the people who were deprived of some of the material, I want to get through all the material here so that they can look at the video for the stuff that we couldn't get through. So we're going to be kind of going through this initial part 1, whereas it took me about half the day the first time. We're going to be going through this in maybe a couple hours, something like that. So I'm shooting for like a quarter of the day. And then I want to spend the majority of the time on the P format. And then we're going to skip down to this part 4 here. And we're going to do some of the fun stuff. So like the other classes, there's a lot of lecture up front, and then we get to fun at the end. So we're going to try to get through the fun stuff. And then we're going to go back to to ELF format as time allows. So the point of ELF is really just to start showing some of the correspondences and similarities between different binary formats. They all sort of have the same job. They're all laid out roughly similar. And so being able to see ELF in addition to P will sort of give you an idea of, okay, well, yeah, they both, you know, have to have somewhere in the header file where they specify this is the first instruction that we start executing. They both have to say, you know, this memory from, this data from file is mapped into memory at this location. All right, as with the other classes, you definitely have to ask questions as soon as you have them, otherwise you will get lost. So, you know, even if it's just to reiterate and reinforce what you think you already know, you know, just make a question based on what you know, and then see if you know it correctly. Otherwise, again, you'll keep getting lost. As with the other class, I'm going to invoke the benevolent dictator clause, and that means we're going to do 2 hours and then 10-minute break, and then it'll be 1.5 hours lunch, and then breaks every 5 minutes, every hour for 5 minutes after that, to the end of the day. All right, I'm going to get some water. So the basics of what we're going to be covering, ideally, well, what the grand scheme of things was, and which we'll see how much we get through, is to cover everything from when you have a C source code file or any, compiled language source code file, and see how it's broken down into data structures, how those data structures are ordered and interpreted in order to spit out some assembly code. That assembly code and data is structured in a specific format, the binary format that the given operating system understands. That's P or L for Mako on Mac OS X. And then how that's actually picked up by the operating system, loaded into memory, and how it does any formatting it needs to do, and then ultimately starts executing the assembly code which is within that. So we're not covering interpreted languages, which is, rather than doing all of this pre-processing to generate machine code, interpreted language is just, you have some sequence of instructions and an interpreter which ultimately is going to just perform some logic based on that. Or we're not also covering software virtual machines, so things like Java or .NET, which are things which they're the in-between between interpreters and compilers. They do a little bit of compilation to begin with, and then they generate an intermediate language which isn't actually machine instructions, and then they have some software which will interpret that. But frequently they'll interpret that and then just in time compile it down to real machine language. So both of those are out of scope, but once you see some of the stuff, it'll be clear how some of those could be implemented as well. And as usual, I guess I didn't put the, why are you taking this class thing on the introduction slide, but of course this is going to be useful for things like malware reverse engineering or reverse engineering of non-malware, just regular software. And I also think it's useful for understanding some attacker techniques, stuff like that. So as usual, what I say is that the more you know about forward engineering, the more you know about reverse engineering. So understanding the process that you get from source code down to an actual binary, that helps you understand how you would go backwards and interpret things. Yep. So whereas I learned some of this material for attack purposes, what I've been using it for most recently is for memory integrity verification and defensive purposes. So there's definitely a variety of uses for this type of material. All right, so this is our high-level overview of what, most people know this to some degree anyways. They know the general gist of how source code turns into an actual binary, but you have a bunch of source code files, and those are fed into the compiler, and for each of those source code files, it generates an object file independently. So it just does, it has its rules about how it's going to break down the source code and how it's going to turn it into a well-formed binary, but it generates them one per source code file. And then each of those object files, which are generated by the compiler, get passed a linker. And the linker is the one who's responsible for taking each of those independent files and putting them all together. So after you pass them through the linker, it basically, feeds them all together and generates a well-formed binary at the other end. So this binary is something which is appropriate for execution on the operating system. And so how you would go about executing it is, you double-click it or you run it at the command line or whatever. And your binary gets passed to the OS loader. And the OS loader is responsible for, if there are any additional libraries or anything that are required by this binary, it will specify it in the binary format. It'll say, okay, well, I need this library and that library because otherwise I can't run. And so the loader is responsible for going out and finding all those binaries, finding all those libraries, loading those into memory, and then for each of those, going out and finding anything they depend on and loading that into memory. So it just does a recursive search over the dependencies for the different libraries for the binary. And then ultimately, the loader gets everything into memory, has all the dependencies into memory, and then there'll be somewhere specified that, this is the first instruction which you should start executing. So the ultimate output of the OS loader is an actual program running in memory. And, most of my jokes are going to be pretty deadpan today, like I said, since I'm falling asleep up here. But, this running program will kill us all. So, like I said, I've never had a compiler class. So, thus you must take everything I have in here with a grain of salt. Mostly, I knew a bunch of stuff about the beginning phases, the lexing and parsing and things like that, and I'd even used that on one security project here. But I didn't know as much about how these data structures were ultimately used to output assembly code. And so I read a bunch on that, and what you see here is the result of me just reading a bunch of stuff and summarizing it. All right, so this is basic compiler overview. Hey, Bo, do we have any pointer sticks or anything like that?
You have a laser pointer.
Oh, that would work. So this is a basic overview that I grabbed from a compiler's book. And we're basically going to go into each of these one at a time. But this entire thing is that initial compiler, whatever it was, trapezoid, on the summary thing. And so there's multiple stages to this in order to eventually get into code. And then we had the linker as well, was just the diamond there. And conceptually, what you can think about here with the linker is that each of those output files has, it has some headers saying how it's specified. It's got some amount of code in it. It's got some amount of data in it. But each of those does not necessarily stand on its own and work as a properly functioning executable. So one object file may refer to data that it doesn't have, which is stored in some other file. So if you're writing a C program and you write extern, so if you're saying, I declare some global variable in, my file 1.c, and if that global variable is then used as an extern in my file 2.c, when each of those is independently compiled, the compiler needs to say, for the first one, it needs to say, I know that this thing is trying to use, some global, but I can't find it within my file, so I'm going to tell the linker, you need to eventually find me this global which my code depends on. And so that global could be in some other things. So between the two of these object files, eventually the linker is responsible for intermixing them, splicing them, is what I said before. Yeah, so it splices each of these together. It generates one final binary with its headers, all of the code mixed together, all the data mixed together. They're all mixed according to having the same permissions and things like that. We'll talk about that later. And so this is the basic job of the linker, is to take anything where references are unresolved within a single file, combine them together into a final file, and fix up any references to data which the individual files can find, as well as the linker is also responsible for any data, any references to functions outside of this file. So if you import a function, so if you're using printf in your thing, you're not actually implementing all the code to write to a screen buffer, right? You don't have to do that, but when you import it, the compiled code is going to say this code depends on some function called printf, linker find me printf later. And so the linker will go around and it'll try to find printf in your existing object files, but if it can't find it there, then it'll put it as an imported function into the final binary saying, at load time, OS loader, you try to find me printf, something like that, and it'll say, and I think it should be in, the standard libc library or something like that. And then, so at load time, this is the basics of the OS loader. You may, have clicked on wikidsuiteapp.exe, and the OS loader will take that and it'll load it into memory at some virtual address. But then the OS loader is also going to consult its headers, and somewhere in those headers, like I said, there's going to be references to, wikidsuiteapp depends on mylib1, mylib2, and libc, something like that. And so the executable loader is then responsible for going out to the file system, trying to find mylib1, trying to find mylib2. And for each of those, then it does the same thing. It maps them into memory at some location, maps that one at some location. It would then recurse down and try to find any prerequisites that they have, anything that my libraries depend on, and it would try to load them into memory. The OS loader is also responsible for setting up the stack and the heap, and those are just set up OS dependently. So each OS is going to have its own different way that it decides to set up stack and heap. But generally speaking, they are somewhere that the stack grows towards low addresses. So you saw in the intro x86 class, right? Stack grows towards low addresses. Heap actually grows towards high, so they're frequently bumped up against each other. Yeah.
Does it always map libcn, or does it try to optimize it?
Well, so I didn't. Right. So I didn't put it on this slide. You know, he asked it, does it always map libcn? It really would be only if it's requesting it. So it doesn't need to map it in. And you know, had I had more room, I would also say, you know, this is also being mapped in. So it doesn't have to always put libcn. And then in question 2, the question was about, you know, does it try to optimize it between different processes, for instance, right? So he has the notion that different processes will be sharing libraries potentially. I'll try to bring up a slide from the intermediate x86 class later to show, well, I don't know. Let me bring that up now. So the one thing I want to say here is that, because I guess there was some confusion on this this virtual memory address space right here. This is isolated to a given process. So part of the point of modern OSs running in protected mode is that they're trying to isolate every given user space process from the other one so that they can't, you know, overwrite each other's memory, cause crashes, stuff like that. So each of these, per our intermediate x86 class, each of these virtual memory spaces is specified by some page tables, and it's just data structures that says, here's how I'm mapping out virtual memory. And then each process gets its own set of page tables, which just means each process has its own mapping of virtual memory. Every process is going to get the same physical memory that backs the kernel side. That'll all be loaded into each process. But then this user space side, the mapping between physical memory and this virtual memory will differ between processes. And so potentially they can share physical memory between 2 different virtual memory spaces. So in this class, we're always talking about virtual memory. This is kind of why I had put the intermediate x86 level of knowledge of virtual memory versus physical memory as a prereq. But let me grab a slide quick, which will hopefully make this a little bit clearer. We talked a bit in the intermediate x86 class about sharing of physical memory. Thank you. So we talked about virtual memory versus physical memory a lot in the intermediate class, right? So here I've shown 2 different processes, and each of these corresponds to one of those colorful processes over there. So you can have, let's see what these things share. Shared library chunk. There you go. All right, so the shared library chunk 1, for instance. Shared library chunk 1 right there. That's mapped to a specific piece of physical memory. So there's only one chunk of physical memory which actually has the library code written to it. And 2 different virtual memory spaces can each have a mapping to that physical memory. So when we were showing those, you know, here's my executable. So my executable would have, you know, some memory space, but that would be different from, let's see, can I put it here? Yeah. So right here, down at the bottom here, we've got process A, so this would be wikidsuiteapp.exe, and then we've got process B, which is helloworld.exe. These are not going to be mapped to the same physical memory, and these are not going to be shared. So here, this physical memory holds process A for wikidsuiteapp, and that will only be in the virtual memory space of wikidsuiteapp's virtual memory. Process B, hello world, that's going to, this one's code is only going to be in a specific piece of physical memory, and that will not be mapped anywhere into this one's virtual memory space. So this is how sharing is done. Some libraries may be shared. The operating system is trying to just make sure that you're never duplicating libraries and having multiple copies of physical memory. So it'll try to just put it into physical memory once and then map it into virtual memory for everyone. So if someone else already has libc open, libc is mapped into physical memory, and then the operating system just says, okay, I got a copy right there. Let's map it in.
Zeno, are you going to talk about ASLR?
Yes. All right, so that was the basic compiler overview. We're going to dig down into each of these. Linker overview. Unfortunately, we don't have a lot going into this. Got to figure out how best to represent that. And then the operating system stuff, and we'll see this quite a bit. All right, well, I've already given some reasons for why I think there's utility in digging down into the compiler. I think the biggest one is just for knowing the forward engineering in order to know reverse engineering, or just because you like knowing stuff. But this has a variety of places that it's used throughout security. All right, so start talking about syntax and semantics. Syntax is basically how you must write the programming language. So some programming language is going to specify you must code everything like this. You must have semicolons at the end of statements. You must have, ifs have parentheses after the if. And so, it's the programming language designer is free to design this any way they want, right? So if you're familiar with some of the languages like Perl or, Python and things like that, they have much more flexible syntax than something like C, right? So in Perl, you don't need to put parentheses around, function parameters or something, right? You can call print, you can just say print and variable, and that's good enough. In C, you must have, printf, parentheses, variable, close parentheses, semicolon, something like that. So syntax is just how the language designer is saying you must specify this high-level code in this way. Semantics, on the other hand, is what the meaning is actually supposed to be. So what the programming language designer is trying to achieve with a given statement. So, whereas the syntax of an if statement may be, you must have the two characters IF, in ASCII code, and then parentheses with or without a space, something like that. So we know this may be the form of an if statement, but the semantics of an if statement are that if the thing inside the parentheses is true, right, then execute the statement, otherwise do not, right? That's the semantics of what they're trying to do. So the thing is, in programming languages, there are compact and well-defined ways of specifying syntax, but not semantics. So semantics ultimately all get specified in some, or both of these will typically get specified in some language specification where it just says, here's how you must write C++, here's all the options for what you can do, and if you do anything outside of this, we're not going to understand it. And then it also has to say, for each of these things that you can program, here's what it really means. So we get into lexical analysis. So lexical analysis is a prerequisite in order to start doing syntactic analysis. So I said there's well-defined ways to write up to specify syntax, and we'll get into that in a bit. But before we do that, we have to actually start from just a plain text file, which is what a source code file is. Start from a text file and get it into some format that we can actually do something with. So that's syntactic analysis. If you've ever heard of tools like Lex, or you may have heard of Lex and Yak, or Flex and Bison, stuff like that. Or Antler is the thing which I had used on the project. These are tools in order to, you can do lexical analysis, and basically what it's trying to do is you have a source code file. It's a sequence of ASCII characters or Unicode characters or whatever, and you're trying to take this stream of characters and turn it into a stream of lexemes, and those lexemes can then be grouped as being called different tokens. So you can have different categories of lexemes. So one may be everything that starts with a number and then goes for anything that starts with a number and is only composed of numbers. You may call that a number as a token, but really the lexeme is just 1, 2, something like that. That's a single lexeme, but you may classify that as a number token. So the specification of lexemes and tokens right now in the slides is a bit lacking, but say you had a statement like index equals 2 times count plus 17. what you could do, in order to do anything with this, we have a string of characters, I, N, D, E, X, right? That's all the machine knows about. It's some sequence of characters, sequence of bits, things like that. So, first it's going to interpret it as characters, and then secondly, what you want it to do is read in these characters and break them up into groups. Typically, these are going to be separated by white space or something like that. So, it may say, okay, well, I got the first character, and I go until I find white space, and now that's going to be a lexeme. And then I go to the next thing, and I go into a white space, that's a lexeme. So then for each of those lexemes, it's going to take them and group them by some category of tokens. And the reason why this is extremely lacking right now is what I should have is just a specification for tokens showing like how this, a token identifier is specified in a certain way, and that way is given by like a regular expression, basically. So if you're familiar with regular expressions, they can specify not arbitrarily complex strings, but fairly complex strings, just patterns that are matching a given specifier. And so each token would basically be given by a regular expression. So it would say everything that is an identifier has this regular expression, everything that is an equal sign has this expression, everything that has an literal has this expression. So I said we can think of, maybe I called this number before, but an int literal, you could think that the regular expression for that might be, it must start with a number, and it must have some series of numbers, right? And an int literal cannot have an A in it, right? There's no, well, could if your thing is smart enough to do something like hex, right? So then you can make the regular expression more complicated, and you can understand, hex numbers or octal numbers or whatever base you want, but let's pretend it's just decimal at this point. So an int literal regular expression may look like 0 through 9, one or more times. So I'm not going to specify the right bits, but there's different formats. So anyways, we break down this sequence of characters into a sequence of lexemes. This could be, one given interpretation of each of those. You would just say, okay, I see it starts with a letter, and then it's all letters. Let's call it an identifier. I see, it's literally the equal sign. We're going to call that an equal sign. And so you can break them down into this. And once you have this, then what you have is a sequence of lexemes, which are grouped as tokens. And you use that in order to specify some syntax. Your syntax is going to operate over a group of tokens. And it's going to say, you must have tokens structured like this, and then this, and then this. And that's the only sort of syntax which I will allow. So moving right along to syntax analysis. Right, so semantic analysis will ultimately be it'll be within the intermediate code generation, essentially. So I said that there's no good way to universally specify semantics. So there is a good way to universally specify syntax, but for semantics, what has to happen is once you have your syntax specified, down here in the intermediate code generation, or if it went directly to code generation, once you do that, the semantics of what you're trying to do is, it comes out when you take your syntax, which is going to be structured into some well-formed data structure. It's going to say, here's the syntax that I was given, and then based on that, I'm going to spit out some code that does something. And it's the program, the person who's generating the compiler, the way that they spit out the code is based on their interpretation of the semantics, basically. So if they think that, if they see in their syntax that I have an if statement here, they're going to spit out the relevant assembly language, which does a conditional check that says, if this thing is true, then do this code, otherwise do this code. And so it's really in the interplay between when syntax analysis turns into intermediate code generation. That's where the semantics comes up. All right, so on to syntax analysis. And just for your own purposes, this is done with tools like Yak, yet another compiler, Bison, which is just the free open source Yak, Antler, Cup in Java. There's a bunch of different syntax analyzers. So we're going to talk a bit about context-free grammars, which are a way to formally specify a syntax. And so these context-free grammars are the way that I said there's a universal way to specify syntax. And it's very powerful. It's actually, it's shown to be, it can specify more types of grammars or languages than a regular expression can. So a regular expression has some types of things it can generate, but a context-free grammar can generate everything a regular expression can generate, plus some extra things on top of that. So that's why it gets used for syntax analysis. So we're going to be specifically talking about buckets north form, so BNF. Yeah. And what you have in the concept-free grammar in buckets north form is you have the grammar specified as a series of rules, where each of them is some number of terminal symbols and non-terminal symbols. So a terminal means this is something for which there can be no further substitution, and a non-terminal means I need to go substitute something in for this. So the basics that these are going to look like, here we have a statement, a rule within the grammar, and right here what it's doing, what it's specifying is these things between the greater than less than signs. This is what we're going to call a non-terminal. And we're saying everything that is a non-terminal must have a rule which specifies here are the types of things that I can fill in for this non-terminal. And this right here is a single one where this is an arrow. So this is not like a dash and a thing. It's a rule is specified that the thing on the left arrow can be turned into the thing on the right of the arrow. So this equal sign has nothing to do with, yeah, I probably need to put that arrow sign in. So this equal sign has nothing to do with like this equals that. It's this assignment can have a single, can be filled in by a variable, and this is a terminal equal sign expression. So in this statement, the equal sign is a terminal. You can fill nothing in for that. It's always an equal sign is an equal sign. And so you cannot have an assignment you cannot have an assignment syntax without there being, you know, something on the right of something on the left of an equal sign and something on the right of an equal sign. So this is what this rule is saying is in my grammar, in my language, I will create things called assignments, and an assignment is defined as something on the left of an equal sign, something on the right of an equal sign. And, you know, that sort of makes sense, right? So if you want to do A equals B, you're going to have an assignment statement. This is going to get filled in with an A, and this expression will maybe be turned into a var, and then that'll be filled in with a B, something like that. Well, it specifies the syntax, and like I said, the semantics it's kind of in here, but remember the semantics it's when you say something, this is the semantics of what I'm trying to do, you're saying this is the purpose of what I'm trying to do. So inherently, just saying, you know, something equal sign something else, that doesn't tell you anything about semantics. You don't know what that's actually trying to do, right? The equal sign could be a multiply in your language. You could semantically say, this character right there, that's a multiply operation. So semantics is not actually captured within this grammar. This is just syntax. This is saying your structure of tokens and terminals must be like this. And later on, the interpretation of that is what is the semantics. So the grammar doesn't capture the semantics because I can reinterpret this. You know, you have overloaded operators and stuff like that. That's where things get, you know, complicated. You can say, I want to treat a multiply like a plus and things like that. Do crazy stuff. And that's you're overloading the semantics. So correct. That's the intermediate code generation. Once we get to interpreting this syntax into various trees and stuff like that, then we'll turn, when that goes into actual assembly language, that's a syntactic, that's a semantic translation, basically. All right. So what I said here, though, so this is just a single rule in my grammar. This is just a rule that says if you ever see the non-terminal assign, this is your options for filling it in. You only have one option here. You can put in a var equal sign expression. And so, of course, we need similar rules that say for var, here's what you can fill it in with. For expression, here's what you can fill it in with. So it's basically just a bunch of substitution rules that you can, that the compiler will go down the line and do various substitutions. All right. And so that previous one, we saw only one possible substitution. In your grammar, you're typically going to have many possible substitutions which the compiler needs to choose between. So how that's usually represented is, here's a non-terminal right here, ident list. And we say that can turn into a, now this is a terminal. It doesn't have those greater than less than signs around it. This is a terminal and this is a token, right? So you had your lexical analysis. It did some regular expression that said, you know, here's how I can specify an identifier. And then what this grammar is saying is, you can either turn this thing into a single identifier, which may be, you know, an A or a B. It could be just some program variable. Or this little, this bar right here, you would use that to separate the different possible interpretations. Say, I can turn this into a literal identifier, which is just some lexeme. Or I can turn it into identifier, comma, and then an ident list. So you can see how this is recursive. And this is an example of how you could potentially make your grammar understand arbitrarily long lists of things, right? So I could, let's see, I'm going to go to the sideboard, Bill. So, you know, I can specify an arbitrarily long sequence of things which my grammar will recognize because I can just do, what was it, ident. Right, and so I can substitute for that and identifier, comma, ident list. And then I can substitute for that. So this is a terminal. This is still a non-terminal. And the point is, in order to actually, for the compiler to ultimately finish what it's doing, it needs to find some way to fill in all possible non-terminals for the sequence of lexemes which you've given it. So that then would turn into, this would still be there. Identifier, comma, and then you could do again. Identifier, comma, and then this again. But ultimately, so here I'm choosing the second rule, right? So each time from here to here, I chose the second rule, and I said I want an identifier, comma, ident list. Here to here, I'm going to choose the second rule again. I say I want identifier, comma, ident list. But then right here, I can choose the first rule, and I can say just put in an identifier. And what I'll ultimately be left with is just ditto, ditto, comma, identifier. Right, so ultimately I'll be left with identifier, comma, identifier, comma, identifier, and that's like a way that you can specify a list in your grammar. Your grammar is saying, I recognize lists of things. This list is specified by this grammar rule. And then just a miscellaneous thing. Typically, I don't think you even see it in my examples, but typically you'll start with some little program, and program will have an interpretation to initial possibilities, and from there you just keep branching out. All right, so here's a very simple grammar for assignment statements, which I slightly modified from this book that I'm referencing. So here we're going to assume you start with an assign, right? So you're saying that this grammar can only recognize assigned statements, right? It can't do anything more complicated than that. It's basically saying you start with an assigned statement. You must have an assignment in this grammar that recognizes assigned statements. And then you can have ID equals sign expression. Your choices for ID are ABC, something like that. And those are each non-terminals. I guess I didn't put them each on their own line here to save space for some reason. Now plenty of space. And then expression can be filled in with ID plus expression, ID times expression, parentheses, these are little parentheses with some expression inside of it, or ID. So what the compiler is trying to do, so you may be, right, so you're programming some code and you get a parse error or something like that. It tells you syntax error, right? You leave off a semicolon, something like that. When you get those parse errors, what the compiler is telling you is, I'm trying to recognize all of your code according to like some huge stack of rules that I have in the back end, right? So something like this, except way, way, way more complicated. And so what it's telling you when it has parse error is, it's saying, you've given me some statement, like this statement on the top here, and it's saying, I tried to create some construction of these rules which ultimately would yield this statement. But if the rules say you must have a semicolon at the end of expressions and you don't have a semicolon, it's going to say, I failed to recognize this. It's going to kick out an error, and it's going to say, try again. So what we're doing here is we're playing the compiler, and we're saying, can I recognize this statement on the beginning? So A equals B times parentheses A plus C. We're saying, is that statement at the beginning within the grammar that we had for the assignment on the previous slide? And it is, as you can see with this construction. And again, as I said, we're going to go fairly fast through this initial stuff, so I'm not going to belabor the point. But we said the assignment, so the assignment, you had no choice. You start with an assign, and you must have ID equals expression, right? But now what we're going to do is we're going to pretend that our compiler is always starting at the left-hand side and trying to fill in the things. Whatever the leftmost non-terminal is, it's always going to try to find something to fill that in. So it has an ID, and there's only, so many ways you can have an ID. And you can have A, B, and C. Those are your only possible choices for ID. And so it's trying to create something which ultimately yields this top expression. So, of course, for the ID, it's going to say, yeah, I have to put in the A, otherwise I won't have A equals something. And so you can see how it just basically goes down the line and fills in different replacements for each of those grammar rules. So for the expression, you can do expression can be turned into ID times expression. Right? And so that's how it finds this star. That's how it gets the multiply. Since ID times expression, and then ID gets turned into V. And so you can see how it just goes down the line trying to find rules in order to fill this in. How the compiler actually decides on which rules to try, right? So you can think of, why didn't the compiler initially try to immediately fill in for expression, parentheses or something like that, right? Why didn't it try that and then go back and say, no, that didn't work, let's try again, things like that. And so a naive compiler will do that, and so in compiler's class, I believe they'll tell you how to, so one, it's outside of the scope of this class. Two, I'm in a compiler's class. So three, what they're going to do is tell you that your compiler needs to do something like look ahead. So basically, while it may be filling in things from the left side to the right side, it may be trying to look ahead some number of tokens in order to figure out what should be coming next. So right here, at this point where it goes A equals expression, and then it has a bunch of different choices for expression, right? It could have tried the plus, right? So for one thing, the order actually matters. So it will start here, and it'll say, okay, well, should I be using this next? If no, go to this next. If no, go to that next. So the order does matter, but it's because of this look ahead that it realizes that it shouldn't fill in the plus, because it basically says, well, if I'm right here and I've got the A equals, and now I've got something over here, if I fill in ID plus something, I'm not going to be able to get that multiply sign. So it basically just looks ahead one symbol and says, all right, well, the next symbol over is a multiply, so I'm going to have to, let's go with this rule. And it could go with that rule, it could be wrong, and it could have to backtrack and stuff like that as well. So there's the possibility of backtracking, but in this case it works out because it's simple grammar. And there's all a bunch of, this is the kind of thing that compilers classes tend to more focus on, is the notion of like what languages can be interpreted with this or that different way of interpreting your grammar and stuff like that. So there's one class of language which cannot be recursive and another one which can, or you can't interpret a recursive language with one type of compiler scheme and not. Anyway, outside of the class. So this is then a parse tree, also called a concrete syntax tree. So all this is really is a tree form of representing that little sequence of statements that we talked about just before. So we said we start out with assignment, and the assignment, so in their thing they were using like Pascal syntax, so they were doing equals with a colon, but assignment must always turn into ID equals expression, right? So that's our first replacement. And then they're doing a leftmost sort of fill-in here. So then they take the ID and they immediately turn that into an A. And then they say, now I have an expression. What am I going to turn that into? ID times expression. So this is just a way of representing as a tree this sequence of statements right here. And the benefit potentially from representing it as a tree is that you can maybe come up with algorithms which then start walking the tree, depth first traversal of this tree, for instance. It will say, well, if I say that it's doing leftmost first, then it is a depth first thing, right? So it's going here, and then it's going to the left side. It's trying to fill that in. It goes down, down, down. comes back up, tries to fill that in. Well, that's already a terminal. Goes back up, tries to fill that in. Okay, you get that, and then it goes down, etc. So putting things in tree format is just good for then ultimately specifying algorithms which walk those trees and figure out how to fill stuff in. Oh, I'm supposed to hide that. Well. So this is a syntax graph. As my non-hidden slide shows, I think it looks like a rifle. I think this is one of the cooler looking syntax graphs you'll find because it looks like a very cool rifle. So a syntax graph, on the other hand, is a way, this is a kind of, I think it's a fun way of specifying a grammar where basically you're saying for the things which this grammar recognizes, just follow the syntax graph or on the tree and stuff like that. So, you know, if I have the number 0.32e negative 62, I don't know, you would start here and you'd say, you know, does this grammar recognize the number 0.32? We'll just say 0.32 for now. Say, okay, well, I can go down here, but that'll give me a negative, so that's not it. Go down here, and I could go right here, but my thing starts with 0.32, so this is only digits 1 through 9, right? So, where is it? Digit 1 through 9. Doesn't have it on here. Basically, this would be, so each of these is basically like a lexeme, right? So I can have a lexeme where it's a regular expression that says, you know, the digits 1 through 9 can be, you know, a single digit 1 through 9. So anyways, I'm trying to get 0.32. I can't go here because that can only create, you know, 1, a 2, a 3, through a 9. If I go right here, and that gives me a 0. Okay, it recognizes 0. And now I could skip over here and go like that, and okay, I can see I recognize just plain 0. But if I want to do 0 point, and then this digit can be filled in with any digit, 0 through 9. So 0 point, you know, 3, and then loop around again 2. And then if I want, I can go down here and I can recognize something E, you know, negative something, or I can just go 0, 3, 2, and then exit out. I successfully walked my way through the syntax graph. Therefore, this graph recognizes, you know, the number that I'm trying to make it recognize. But you can see how this, you know, I said before, right, you could have rules which can start recognizing, you can recognize just plain decimal numbers, or you can start recognizing like hexadecimal numbers, right? So hexadecimal would imply that your grammar and your syntax graph would have one path on it where it starts with 0x or something like that, or maybe it ends in h, something like that. So wake up. All right, so syntax graphs, yes, syntax graphs are great. I love syntax graphs. All right. And so, but again, the syntax graph, really all it is a way of visualizing a grammar. We have a grammar over there to the side, and now unfortunately the grammar for JSON is not specified in Bacchus form, so we don't have those greater than less than signs on each side, but you can see the way the tabbing is specifying it, that it's basically, you know, a number, that's a non-terminal, an int is a non-terminal, fract is a non-terminal, an x is a non-terminal, digits is non-terminal, e is non-terminal. And then each of these things underneath e can be filled in with an actual terminal. So that's a terminal, etc. So basically it's saying you can take number and you can go to just an int, where int is defined here, or you can go an int space fraction, or well, there's no space actually, int fract. So you can do some digit and then dot digits, something like that. So it's just specifying I have some grammar, and this is the way that I can walk my way through the tree. So I was going to put that as just a miscellaneous sort of. So the miscellaneous use for things like context-free grammars, basically. So we're skimming over it in service of understanding the way the compiler breaks down the C source code file or something like that. But you know, once you know things about context-free grammars, you'll find that it has broader applicability, like you know that JSON graph that I just showed. Right, so if you go to the JSON website, you'll see that they actually have specified the entire grammar on this right-hand side. This is the entire grammar for everything which a JSON object can be structured as. So this is the only way that you can structure a JSON object, and it's fairly limited. You can see like half of it is just this number thing right here, right? You get rid of that number, pretty much this. You got characters. Okay, that's characters it recognizes, and then just a fairly simple structuring of objects. So you can have curly brackets with nothing in it, so that's an empty object. Or you can have curly brackets with members in it. Member can have a pair or pair comma member. So here's basically that recursive thing that we saw with the ident list. Members can recurse back to members, and so you can specify an arbitrarily long thing of pair, comma, pair, comma, pair, comma, pair, comma, all of within some curly brackets. And then a pair is just a string colon value, right? So you can see how this will let you send a bunch of data where it's string colon value, comma, string colon value, comma, etc. And so very simple. This is why I'm saying I think syntax graphs can be elegant, right? So this is just the way that you specify your data. Nice. Look at that. And then it's all nice, and then eventually you have the right colon, so it's cool. All right. SQL grammar. So this is what I actually use context-free grammars for. Okay. So if you go look at like the grammar for like SQL statements, well, so this isn't a grammar. This is trying to tell the programmer, here's all the different ways that you can actually specify a SQL statement. But it turns out this is basically a context-free grammar in that, the select statement has to start with a literal select, but then you can have optionally, so within these square brackets, these are each optional things specified by each of which is a possible fill-in. So you can do select, all, or you can do just select, right? So everything in here is optional, and you can have one of these three optional things. That's optional, etc. But then eventually you have another, like, this is required select expression. And so they'll have some definition for select expression later, elsewhere. And you can have, see how they're specifying right here. This is not, grammar in the sense of it's not structured in like the bucket store form or even in that JSON sort of form, but you can see how they're basically specifying. This would be like that recursive type specification, right? They're saying you can have select expression, and then optionally you can have comma select expression dot comma select expression comma select expression dot dot dot. So they're saying then you have an arbitrarily long list of select expressions, etc. So where I use this basically is I actually had to write a grammar which recognized SQL statements in order to, it was for a research project where we were trying to randomize the syntax actually. So in order to do something like preventing buffer overflows, preventing SQL injection exploits, we wanted to randomize the syntax so that, an attacker knows the basic syntax of SQL, and so when they do a SQL injection, they're sticking in, a single quote or something like that in order to terminate out some field, and then they add in more sequences on after it. So they do like, and. So they'll use like an and then some other sequence of statements. If you randomize the terminals essentially in a SQL statement, then when an attacker injects some code, it won't actually match. Well, if you make your parser have a requirement that all of the terminals must be matched up on some random number, for instance, and when an attacker injects SQL, if he doesn't know the random number, he won't have injected the correct terminals. Therefore, your parser will just kick it out and say, yeah, sorry, I don't recognize your SQL because my select is actually select underscore random number 1, 2, 3, 4, 73. And then I expect from to be from underscore 1, 2, 3, 4, 73, something like that. So all of my select and my from and my and my where, all of that, they all have to have the same random number on it. So if some attacker injects SQL statements which don't have the right random number, then it'll break, so it becomes And then also, another random use is that actually there's a extended bucket store form, which, I have it there. There's actually what's called extended bucket store form, which is used in like RFCs. So the SIP protocol, that's redundant. SIP within the RFC will say, here's all the possible ways that you can actually specify a message for SIP, right? So using voice over IP and things like that. And they specify in an extended form of buckets NOR where basically they're just trying to make it more compact by using things like those square brackets in order to say stuff between square brackets is optional, etc. But let's see. Let me see this thing. So basically, there's an RFC for SIP, and they specify in bucket store form. This website is basically just pulling it out. Oh, augmented, sorry. I called it extended. There is extended as well, but for the RFCs, they typically call it augmented bucket NOR form. And there's actually an RFC specifically specifying what the format is for A, B, and F that they use in other RFCs. So, but basically, you have a SIP message, and it can have, request/response. The format, so the slash here means or, basically, in their format. They're saying your SIP message can either be a request, and there'll be some definition of request, or it can be a response, and there'll be some definition of response. So here's the definition of request. It's saying if you have a request, it has to be filled in by a request line, and then 0 or more message headers, and then a control character return line feed, and then message body, something like that. And so you can go to each of these, and the nice thing here is you click through, and for each of these non-terminals, you click through and you see how it's actually specified. So request line must be method, and then a terminal, SP, and then request URI, terminal SP. So you say, what's a method? And you go here. Okay, well now we're starting to get into some things that look like you might use in a protocol, right? So going all the way back, right, we know we must start with the request line. We know the request line must start with the methods, and we know the methods are of the form invite, M, ACK, M, options, M, etc. So you know now that the SIP message must always start with something like invite M, ACK, M, options, etc. So by just understanding what forms this grammar specifies, you can say here are all the possible values which a SIP message can have, which a SIP parser should understand. All right, so those are just some miscellaneous uses for miscellaneous security uses for context-free grammar knowledge. All right. So now what we saw before were those parse trees where I just literally took that filling in the different rules and turned it into a tree. We called that a concrete syntax tree or just parse tree. So abstract syntax trees are basically a simplified form of concrete syntax trees, and they're more convenient to work for. There are better forms to put stuff into in order to make more simplified algorithms to walk the trees and generate code and stuff like that. So let's see. And this is just my funny little thing here that you have to actually know about abstract syntax trees in order to understand this Brack article where they're talking about how they're proposing hacking GCC in order to make it not do integer overflows, basically. So that's just a miscellaneous you can read later. All right, so an abstract syntax tree versus a parse tree. The key difference here is that parse tree was just that literal translation of those the grammar. The abstract syntax tree, the operators are always interior nodes on this tree, and the operands are always the two children trees, essentially. So also the depth, therefore, specifies order of operation, stuff like that. So what I can see immediately from this tree is that the deepest stuff must happen first in order to process the upper stuff. So the fact that there's an A plus C down here at the bottom part is saying that you take, the A plus C, and then ultimately you take B times the result of that A plus C. And so you can have algorithms which, well, we'll see it in a little bit, so I won't jump ahead. So basically the main thing you want to know about an abstract syntax tree is that the interior nodes are the operators. It's saying, if I've got two things hanging off of a plus sign, I'm going to be doing a plus operation on those two operands on either side. And therefore, it's by putting it in that way, by putting it in that form, it basically makes it, as you can see, much more compact than the concrete syntax tree. And actually, let's see, I don't know whether it's worth saying, but you know, for all those people who know and like functional programming languages and stuff like that, things like Lisp and Scheme and whatever else is a functional programming language, they were all based on, so when the computer scientists back in the day were having all their fun with finding the different ways you can specify languages, what they found was that the abstract syntax tree was extremely useful in order for these functional programming languages, because basically by using this, the things like Lisp and Scheme, they, I don't know if I can finish this thought really. I don't have enough brain power right now. Yeah, I'm going to leave that thought off. All right. Here I just wanted to do a quick example of a little bit more complicated and simultaneously realistic parse tree and abstract syntax tree. So you can see how this grammar over here, it's not fully specified, so it's missing a bunch of chunks, but this grammar over here, roughly speaking, recognizes these statements on the right. The statements on the right, as you can see, look pretty close to C-style code. The main difference here is that these, for their functions, this fun is not like a return value like in C. They're just saying literally, in order to figure out that there's a function here, I'm going to require that you must have fun and then the name of a function. Something like that. So they're saying in my grammar, in my language, you always put fun and then the function name and then some parameters and stuff like that. And so given that sort of syntax, well, this grammar specifies that sort of syntax. So you see down here, this function definition is fun and then ID. So it's saying, you know, in my grammar, you must have, in order to have a function, you must have fun and then you must have fun and then ID. So given that grammar, it recognizes, you know, it's not fully filled in, but it recognizes this sort of stream of tokens and things like that. So the main thing I wanted to show here was just a more complicated one to say it's more realistic, because when we eventually get to the things, abstract assembly trees, which spit out assembly language, you'll want to know that we're not just dealing with these toy examples of A plus B equals C, stuff like that. So the concrete parse tree for this previous definition here, right? We're taking this, we're saying, you know, you can have some list of functions. So we've got a recursive sort of listing thing as before. And so it's saying you can have function list, can have function definition, and then another function list. So that's, again, the recursive. You can have any number of function definitions by just filling this in. And then for each function definition, it is just a fun and then ID, parentheses, and some parameters. And param list, as you can see, is not specified right here. And then body, and body is just curly brackets and then whatever statement is. So basically, we start with the program, and then we said that function list can have some arbitrary number of functions, and here it has 2. So first you filled it in with function definition and then function list, and then that function list we filled in with just a function list. So that's how we get our list of 2 function definitions. And each of those function definitions must have the form fun and then ID. ID here was main. Parameters, this first one, main, had 0 parameters, so that's saying that's the empty thing. Right there we see there's no parameters for main. So basically for parameters it fills it in with epsilon, I think is what that is, which is the empty string, just saying got nothing there. And then body is curly brackets, and it would be some statement list, which they don't show. Same thing over here. This was the more complicated one. We had function foo, and then parentheses, some parameter. It had int n. Then you have body, parentheses, and it had n equals n, whatever, op1. I don't think that's what it had, but n equals n plus 1. All right, so that was the concrete syntax tree. Is just, you know, filling in each of those rules. This abstract parse tree, unfortunately, is not exactly in the way that we're used to looking at it. They're basically showing it as if you were if you were writing your own sort of tree library, right? You have to have some way of specifying a tree in terms of links off of data structures and stuff like that. But the point here is the operators are still the internal nodes, things like that. So we've got function list. It can have function main, function ID, and those are the internal nodes. Then for each of those, you have subtrees. So you have a subtree for the body there. it would have had a subtree for the parameters if it had it, but it doesn't have any parameters. So this would have, main would have went, parameters and body. Foo has parameters and body, and then, body will ultimately have, whatever it's filled in. You'll have some list of assignments, or some statement list, and here the statement list was just an assignment of n equals n plus 1, something like that. So still, the point with the abstract syntax tree is it's actually still much more compact than the full concrete syntax tree. And your internal nodes are your operators, and your trees below those are the operands. All right.